principal ideals.
Thank you. I'd like to thank the organizers for inviting me to give this talk. This work is with Ronald Kramer and Leo Duca at CWI and Oded Regev at NYU. So I'll take it pretty easy. We won't be too technical in this talk, but we're back to lattices, and we saw a lot of talks and very interesting crypto you can do based on SIS and LWE and the ring versions of these and ideal lattices and so forth. But these problems haven't taken over the world entirely. There are other lattice-based or lattice-related crypto systems that don't rely directly on these LWE and SIS problems. And in particular, a few recent crypto schemes, including Smart Verkauteran's simplification of Gentry's original FHE, the breakthrough Garg, Gentry, and Halevi multilinear maps, simplification of that due to Langlois, Stelle, and Steinfeld, I think. And then this paper by Campbell, Groves, and Shepard, who normally don't publish because they're part of the GCHQ, the UK's NSA, right? So all of these papers, maybe not independently, but semi-independently, proposed crypto systems that share this common element of how they generate keys. So to generate a secret key, they will fix some ring. So for example, our favorite power of 2 cyclotomic rings here, ZX mod x to the n plus 1 for n to the power of 2. And the way they choose a secret key is to just choose a short generator, short element rather, G, in that ring. Okay, so from a Gaussian distribution or something like that. Reasonably short, not too short, but not very long either. And then as the public key, they output a bad basis of the ideal generated by G. So this all multiples of G in the ring, you can compute efficiently a bad basis. For example, the Hermite normal form is sort of the worst possible basis you can give out, or the baddest basis you could give out for that ideal. So the public key will be this basis B, and the secret key will be this short element G, or the short generator G of the ideal. Okay, so if you wanted to cryptanalyze or try to break these schemes, here's one way you could do it in 2 steps. The first step would be to solve what has been called the principal ideal problem. So that says, given this integer basis B of this ideal I, let's first try to find some generator of the ideal. Okay, so find some generator H. Maybe it's not short, okay, but it generates exactly those elements in the ideal. Okay, so the ideal I is H times R. Okay? And then anyone want to guess what step 2 is? Let's make the generator short. Okay, so let's solve the short generator problem. I'm just making this name up. It's not really standard, but this problem is, okay, given an arbitrary generator H of a principal ideal, let's recover the short generator G up to trivial equivalences like, well, negative G is just as good, right? So, and there are other symmetries that don't cause any problems. So this is one way you might go about attacking the scheme. Yes?
Isn't any short generator of I good enough?
Yes, exactly. So actually, thanks, Vika. I'll pay you later for the question. It's actually not obvious a priori that G is even uniquely defined here. I mean, there could be 2 generators which are short enough or equally good, or maybe there's another generator that's even shorter than the G you chose. So it turns out that really any short enough element of the ideal suffices to break these schemes. So you don't even need to have a generator necessarily.
It has to be, right? That's the only connection between the secret key and the public key.
Not necessarily. I mean, you could decrypt using any short enough vector in the ideal. It need not be a generator, right? But in fact, we will show, or we'll see that in fact G is uniquely defined, which is somewhat surprising, and that there are ways to recover that G up to these trivial equivalences. Okay. So we'll be talking about these 2 steps. Right now, and let's just see what does it cost to do these 2 steps. So the first part, that is given this basis of the ideal to find some generator H, not necessarily short. So this has been investigated reasonably well over the past couple of decades. It's not the most popular problem ever, but there are, it shows up in books here and there. So the best state of the art right now is that you can do it in sub-exponential time, about 2 to the n to the 2/3. Via a classical algorithm by BS and Peikert, and followed up by BS just about a year or 2 ago. And at the same time, there has been major progress toward a polynomial time quantum algorithm to solve this. So that follows from work by Eisentrager et al. Recently, B.S. Song, and also the folks from GCHQ that I mentioned before. So the exact status of whether this is solved or not is a bit unclear. Depending on who you ask, they say it's definitely solved or it might be solved, something like that. So I'm not the person to ask about this, but it seems to be very plausible that there's a polytime quantum algorithm for this phase of the attack. Was there a question?
My question was what?
Yeah, what do I mean by major progress? I don't know. So keep an eye out, but I don't think it'll be too long before this whole thing will be resolved one way or the other. Okay, so then the second part of the attack is the short generator problem. So given this generator H that you found, let's convert it to a short generator. And what we'll see is that in general, given any generator of a ideal, to find an equivalent short generator is essentially the closest vector problem on something called the log unit lattice of the ring. And I'll define this and I'll give pictures of it. And Demian actually foreshadowed a little bit on this. But in fact, what has emerged from the past couple years as people talk about these crypto systems is, in fact, it's actually a potentially easier problem than arbitrary CVP. So you could throw Noah and Daniel and Devesh's CVP algorithm at this, but it would be exponential time. But actually, what we have is something called a bounded distance decoding problem, at least in our cryptographic setting. Okay? And so I'll give more details on this, but the upshot is that the fact that there exists an unusually short generator G for our ideal means that actually we're in this bounded distance decoding regime. So we don't have an arbitrary target that we have to decode on the log unit lattice, but rather we have a point which is, say, unusually close to that log unit lattice. And that turns out to make a huge difference in what we're going to be seeing. All right, so this Campbell, Groves, and Shepard paper had a very surprising claim in it, that they said, oh, actually, the short generator problem is easy in power of 2 cyclotomics. And that's pretty much all they said, which was not so believable to me. I had thought about this question a little bit before, and then their paper came out, and there weren't any details, so I didn't change my opinion after reading the paper. But it turned out they were right. So we asked them, and they gave a few more details, and they said, yeah, we ran experiments and confirmed that this works. But there really weren't. There was no explanation of what's really going on, and certainly nothing theoretical that we could hang our hat on to understand really what was quite going on here. So that is basically the goal of and the purpose of this present work, is to actually make the second claim rigorous and to prove it. And so what we show is that in this cryptographic setting that I showed you, where you generate keys in this way, the short generator problem can be solved classically in polynomial time for any prime power cyclotomic. So we generalize a bit beyond power of 2 to prime power cyclotomic rings.
This is once you're given a principal ideal?
So the problem is you are given you're given H, exactly. So you're given H and you want to recover G. And we're in the cryptographic setting, which is shorthand for you know that G was generated, say, from a Gaussian or as a relatively short element.
And so just to check if I understand, so your message is you think these crypto systems are broken, you shouldn't use them?
Right. So what does this mean for ring-based crypto? Thanks.
But the part 1 is still
Quantum range.
Yeah. So part 1, well, let's say what does it mean, right? What are the consequences?
An exponential algorithm to find classically the generator.
Yes.
So even classically there are strong implications.
Right. So for what does this mean for those systems and for ring-based crypto more generally? So the 4 works I referenced, they're obviously weakened classically. Now we have a rigorous sub-exponential time attack in the dimension. So if you were hoping to use moderately small dimension like 256 or something, that's probably not safe. And then they're quantumly broken modulo the exact level of how well this quantum result has been established.
You're always finding the same G.
Yes. So we'll recover the secret key, up to these trivial equivalences, plus minus and things like that.
Does it work for larger P, or P is assumed to be polynomial in theorem?
P, in order for these systems to make sense, the dimension has to be polynomial. It has to be pretty small. The polynomial. There's no characteristic anywhere in here. This is just we're in the mth cyclotomic for some m which is reasonably small in the hundreds or thousands.
No, in the theorem in the previous slide.
In the theorem, okay, here.
You're saying it works for any prime power cyclotomic.
Yes, any prime power. Yes. So P can be a large prime as long as P to the k is small enough that you can actually write down ring elements. The theorem holds, right? So what does it? Going back to what it means. Obviously, those reference works are classically weakened or quantumly broken, perhaps. That's the bad news. The good news is that the rest of ring-based crypto seems to be unaffected. And the reason is basically its security is lower bounded by harder, what appear to be harder, certainly more general problems. So here is kind of an artificial landscape of the kinds of problems that you might consider using or being useful in crypto. So on the left we have, what are these acronyms? The shortest vector problem on principal ideals that are guaranteed to have a very short generator, unusually short generator. Okay, so this is the problem that has now been attacked. Okay? So this one you want to scratch off your list. But if you slightly generalize the problem or just consider a wider class of instances, such as the shortest vector problem on arbitrary principal ideals, this attack doesn't seem to work at all. The main thing that makes this attack work is the promise that there's this exceptionally short generator in the ideal.
What exactly do you mean by exceptionally short?
I'll say more in a second, yes, but let's just call it exceptionally short for now. Yeah. Okay, so as soon as you generalize to, say, arbitrary principal ideals in the shortest vector problem, we don't know how to break that. Obviously, a more general question beyond that is shortest vector in any ideal. And this is the problem that, or any ideal in the ring, and this is the problem that we can reduce to ring SIS and ring LWE and so forth. So the red seems to be comfortably far away from the crypto part here, at least for now.
So
yes.
If you put less or equal, you should have, didn't even to put less at least in one of those inequalities? Or?
Well, these are reductions, right? These are things I can prove as reductions. So, yeah. I mean, you want me to prove P is different from NP, or?
Well,
Yes.
Yeah.
No, but
I'll do it if you want, but.
My question is the belief that each of them is significantly more difficult? Or
Oh, belief. Yeah. Okay, so, I mean, this is a personal belief, but obviously I think that this is probably a strict inequality here, at least given what we know how to do. From here to here, I'm not so sure if it's strict or not. There are reasons to think maybe it's not, maybe they're equivalent. I'm not clear. From here to here, actually could be strict as well. We don't know. If you gave me an oracle for SVP in ideal lattices, I still wouldn't. I don't know how to use that to break ring SIS. So there could be strictness here.
So
There's probably no strictness here.
So the belief is really the first one should probably be strict, but you don't know.
Yeah, I think probably this one is strict, and this one is a good chance of being strict. Yeah.
And crypto here just means some crypto, right?
Yeah, I mean any crypto that's built on these problems, right? Yeah. Okay, so I already said it, but I'll just put it on the screen now. So the attack, the reason the attack works is really crucially relying on the ideal having this exceptionally short generator. And just to give you a flavor, these ideals are actually extremely rare. So if you look at the set of all principal ideals in fixed ring, for most of these ideals, the shortest generator in the ideal is actually vastly longer than the shortest vector in the ideal. So having a short generator is actually useless to you as the attacker. You can prove this, yeah. This is you can formalize it.
Can you quantify the bus?
Yeah, you can quantify it. It's like at least 2 to the root n factor.
Not
I can, yeah.
So vastly is in terms of n.
In terms of n, it's about 2 to the root n factor worse. Yeah. Yes.
Coming back to the previous line, does the choice of the ring matter?
Sure. Yeah. So all of this is predicated on fixing a ring, and cyclotomic rings are the most popular. And then all of these reductions hold for any fixed cyclotomic ring.
But outside these rings?
Much less is known. Much less is known. Well, I mean, all of these will hold for essentially any reasonable ring that you choose. So this sequence of reductions holds for any reasonable ring. But I don't even know if it's red on the left.
What about non-principal ideals where the generating set is tiny? Is that closer to this?
Non-principal ideals where the generating set is tiny. What does it mean?
Both generators are small.
Oh, so the pair, well, that actually doesn't happen. I mean, the canonical way of getting two generators is one of them is the norm of your ideal, which will tend to be enormous. Maybe there are other ways of getting two, but usually you don't present an ideal in this way in a crypto system. I mean, you can, but most systems don't. So, Damien, you had a...
You can always represent the ideal with two short elements.
You cannot. Yeah, that's what I was saying. One of them will be the determinant, right?
No,
you cannot. Okay, at all. Good.
No, you cannot.
You can. Okay, you can. You can. Okay.
About Minkowski's bound.
I see. Okay. So in that case, I mean, if you give me two short generators, yeah.
Are they easy to find?
No.
Right.
It's not if you restrict to ideals that have
two short generators.
You don't restrict anything because they always have two short generators.
So maybe that'll be open problem 2.5 at the end or so. Yeah.
So wait, so what's the difference between that when you have only one generator, then asking for that one generator to be short? That is a restriction, but not in the case where you have two generators.
It's not a restriction.
Not a restriction. Okay.
Okay. So there is a gap between 1 versus 2 in that way.
It would seem so, yeah.
Yeah.
Okay. Okay, so maybe the lesson that I take, at least as a biased observer, of course, is that it seems like devising hard distributions of lattice problems is really tough, especially if you want to embed some kind of trapdoor information, that lets you decrypt or something like that. So Daniele's talk also had, the fall of lattice crypto systems in the 80s, where everything people proposed ended up getting broken because of this hidden structure. So it seems to be very tough to do, but this is where worst case hardness proofs really kind of show their value. They provably protect you from weak instances, or from generating or using weak instances. So if you use the distributions given to you that have worst case hardness, you're not going to end up relying on a problem that is much easier than you thought it was, or at least a much more specialized version of the problem. Okay, so we should get to some technical content. So I want to show you just the main ideas, the geometric pictures of the log unit lattice, and then a quick outline of the attack and how we prove it. But I won't be able to say too much about how we prove it. Okay, so we're using this object called the log unit lattice. And in order to define this, we need to talk about embeddings. So we've seen this once or twice earlier in the week. But in case you don't remember, so if you take a number field k, we can write it as the rationals with an indeterminate x modulo some polynomial f, which is irreducible over the rationals, and it has degree n. And so we have these things called the complex embeddings. So these are the functions from, these are injective homomorphisms from the number field into the complex numbers. And basically, they just send x to each of the roots of f. Okay, so we have n of these embeddings, one for each root of f. They basically correspond to evaluating the polynomial at that complex root. And so the canonical embedding maps you from k into c to the n, where you simply put all the evaluations. You just evaluate all the embeddings on the value x. And I'll show a picture of this on the next slide. So that's standard stuff. More standard stuff is this thing called the log embedding, a logarithmic embedding. And this maps you from the number field -0 into the reals, n-dimensional reals. And basically all you do is take the log of each of these embeddings, each of these coordinates. Well, you can't take logs of complex numbers you can't get a real number out of it. You take the log of their magnitudes. Okay? So we take log of sigma 1 of x magnitude through log of sigma n x. And as you know, when you take logs, it converts multiplication to addition. Right? So this is a group homomorphism from the field minus 0 under multiplication to addition in r to the n. Okay, so you can just see that's because multiplication here becomes multiplication coordinate-wise here, and then when you take magnitudes, that's multiplication, and then taking logs turns it into addition.
Is the image a lattice?
Yes, it is. Well, not of k. The image of k minus 0 is not a lattice, but for the ring it will be. Yeah, we'll see it in a second. So just for an example, our power of 2 cyclotomic, the embeddings simply map x to odd powers of the 2nth root of unity, principal 2nth root of unity. So omega to the 1, to the 3, to the 5, and so forth. Okay, so just to give us some understanding, if I take the log of any power of x, the log embedding of any power of x, I just get all zeros vector. Okay, that's because x to the j, well, I replace x with omega, which is a root of unity. Any power of a root of unity still has magnitude 1, and log of 1 is 0. And so all of these logs are 0. Log of 1 minus x is a little more interesting. I was going to write it on the whiteboard, but let's skip it because we have a better picture anyway. So here's pictorially what the embedding and the log embedding look like for the ring z adjoined square root 2. So this is not a cyclotomic ring, but cyclotomics are too high dimensional for me to put them on the slide. So the x-axis is our first embedding. That maps a plus b root 2 to itself. And then sigma 2, the y-axis, is its conjugation. So it sends a plus b root 2 to a minus b root 2. So if you take the element 1, it gets mapped to 1 comma 1. That's here. If you take the element root 2, it gets mapped to root 2 negative root 2, which is down here, and so forth. So in this ring, z adjoined root 2, you get this nice lattice structure under the embedding. And multiplication is component-wise, or component-wise on the x and y axes. So we have symmetries. This lattice has symmetries, multiplication by minus 1 and by 2, root 2 rather, and conjugation is another one. But here's what I really want to show you to get some better intuition. So ignore this line about blue. What we have are units and more generally isonorms. So we can partition the elements of this ring according to their norm. Okay, and their norm is just the product of the two embeddings. So in this case, it's a squared minus 2b squared. Okay? And so all the elements that have norm 1 or minus 1 are on this red hyperbola, which is just xy equals 1, right? Or xy equals minus 1 over here, and these hyperbolas here. Okay, so you can see some elements on these red hyperbolas down there and there. And then elements that have norm 2 or 4, you can see on each of these isonorm hyperbolas. So any questions about this? Okay, so it's a nice picture. Let's now take logs and see what happens. So on the left is just the picture I had before. And when we take logs of the magnitudes, we get a picture that looks like this. Okay, so these hyperbolas now become straight lines. They become log x plus log y equals log of some integer. So what we see here is that the units, the blue points on the red hyperbolas here, become now the blue points on this line of x plus y equals 0. Right? And, well, look, it's pretty nice, right? It seems to be a lattice. That's interesting. And then all these others, so in fact it is, it's a rank 1 lattice. So the blue points on the red line is a rank 1 lattice of in R2, and it's orthogonal to this 1, 1 vector here. If you look at these other isonorms, these other lines, what you see is that for any particular line, you have a finite number of shifted copies of the lattice that's in the red line here. Okay? Sometimes it's 1 copy, sometimes it's 2 copies, sometimes it's 0 copies. For example, there's no element that has norm 3 in this ring. Oh, wait, is that 3? 3? I can't count, but I think that's right. Yeah, norm 1, 2, 3. Yeah, so some of these may be empty. Okay, so that's the picture. And now we can actually make this a bit formal, like Daniele asked. So if we take the group of units, multiplicative units, we call that our times or our star. And then we say let lambda be the log embedding of this set of units here. And so Dirichlet in the 1800s gave his famous unit theorem, which says that our picture, our understanding is what you think. The kernel of the log is actually just the roots of unity in R. So that's something not too exciting, but it's like we saw, right? Log of x to the j was always 0. Those are the only kinds of elements you have in the kernel of log. And more usefully, the image under the log embedding of R star is a lattice that has rank R plus C minus 1, where R is the number of real embeddings and 2C, we have C pairs of complex embeddings. So good, we're going to use this fact that this really is a lattice. And we can now cast the problem of finding a short generator as a CVP type problem or a decoding type problem. So the statement is the following. Elements G and H in the ring, when do they generate the same ideal? They generate the same ideal if and only if they differ multiplicatively by some unit. Okay, so every element, every multiple of G can be written as a multiple of H and vice versa. So there's to be a unit ratio between them. If we take logs of this relation here, we just get log G is log H plus log U. Log U obviously lives in this log unit lattice lambda here. So log G just lives in log H plus lambda. And if we're interested in a smallest generator, so G is a smallest generator if and only if log G is a smallest or shortest element in this coset of lambda, of the log unit lattice. And I put quotes around these words because it's a little bit of a lie, or there's a little imprecision there, but that's the intuition. Right? So if you can find a short element in this coset, you've found a short generator. So that's what we're going to try to do. And I won't show the algorithm because there's no algorithm. It's just, well, you'll see. But we can do it by picture. Okay. So this is what we do. Again, this is our picture of the embedding without logs, and this is the picture with the logs. And so I want you to imagine the following experiment. We pick the generator G, okay, to be relatively short or from a Gaussian of some width. And then I don't tell you G, but I tell you some H, right, which generates the same ideal. Okay? So we know that G and H live on the same isonorm. Okay? So they live on the same line here, right? So I tell you H, and maybe H lies way, way up here or something like that on that line. Well, how do you find G, or how do you hope to find G? Simply, you want to translate H by some points of the log unit lattice. Translate it to bring it into maybe this region here. Okay. So this beam of light here corresponds to the floodlight that you see on the left there. Right? So the bottom line is this is a fundamental domain here. This range from here to here is a fundamental region of the log unit lattice. So if your original generator was anywhere in this floodlight area, you would recover it, okay? Because I would give you this H, it would be way out here, but you would bring it back, into here, which would be in this floodlight region. Is that clear? Does that make sense?
Any G in there is qualifies for you, so it's not a unique G.
Right. Yeah. So the question is, could there be, two G's that generate the same ideal that both live in the floodlight region? It turns out that that won't be the case for typical distributions. Yeah, it won't be the case, which is, yeah, it's just sort of counterintuitive. It's very counterintuitive, but it happens to be the case. So the point is, if you can bring your point out here back into the fundamental region just by shifting it by lattice points into this region, and your original generator lived in this region, then you've recovered that generator, and you're done. So you don't have to use, I mean, this is the best fundamental region to use, but if you use something else, something we shifted over here, it would change the set of generators that you're able to recover or not. Right? But the most natural one is to use the centered beam of light here. So that's the algorithm. There's really nothing to it. What you have to show is that it actually works, which is more interesting. So this is only the one-dimensional case, right? We have a one-dimensional log unit lattice here. There's only one meaningful basis of it. In general, if you want to solve CVP or BDD, you need to have some kind of good basis for your lattice that you're using. So the simplest algorithm says, okay, given a basis and a target, just kind of take the fractional part of the target's coefficients and then return that to bring it into the fundamental region of your basis. So that's all this does. And what you can show, it's a homework exercise, is that if your original generator or your error term, the log of it, satisfies this, so the dot product with the dual of the basis vectors is between -0.5 and 0.5, then you actually recover the generator. So this is just simple homework. And so what we have to show is that that's the case. So our overall analysis, or the outline of the proof, is as follows. First, we need to construct a basis B of the log unit lattice. Okay? And this is not entirely trivial. In fact, it's an open problem how to do this. But there's an almost basis. Okay? There's a basis if you crack open your textbook. There are these special sets of units in the cyclotomic ring, which are almost a basis. They generate a very, very dense sublattice of the full log unit lattice. And it's an open question for at least 100 years to actually compute and find the full group of units. So in terms of conjectures, it's conjectured that these guys generate almost all the units. In terms of conjectures, the hierarchy that Yevgeny told us this morning, he made up a conjecture that he's willing to believe. This is a conjecture made up 100 years ago. I'm willing to believe it. Okay. So that's one little technical piece. Now, once we have this basis, or almost basis, we just have to show that it's good. That is, that all its dual vectors are relatively short. And it turns out this basis is really, really good. It's like vastly better than we would even need to do things. And then we just have to show that if you choose a generator according to a Gaussian or relatively short, that it satisfies this condition so that you do decode and get that generator out.
So what is the conjecture that this set of values is a basis?
No, the conjecture, well, in a power of 2 cyclotomic ring, there's a conjecture due to Weber that this does generate all the units. In non-power of 2 cyclotomics, that is known to be false, but it generates a sublattice of very small index, like 5 or 3, really tiny, and that's enough for us.
But if they are short, even if it doesn't generate, isn't that enough to solve PDD? As long as
no, it's not enough because the H that we get is shifted by an arbitrary unit. So it's not what you think that way. Yeah. Okay, so we have to do 1 has been done for us. We have to do 2 and 3. To do number 2, you break open your textbook by Serge Lang or Washington, and you find the proof that that these generate a finite index sublattice of the units, and then you look in the proof and you realize that there are tools in there that let you actually understand the geometry of these basis vectors. Okay, so, and things behave really well. These vectors, these dual vectors, are roughly 1 over root m, where m is the index or the dimension of the ring, and that's way, way better than you need. And then this is similar when you're talking about logs of Gaussians, and you need to see how they project onto these vectors here. Okay, so I'm a little over time. I'll finish with 3 open problems in order of difficulty. Easy would be to say, let's extend this to non-prime power cyclotomics. This formula doesn't work to give you units like you want. when it's not a prime power. There are other formulas. You could see how the geometry looks for those formulas. It's probably a worthwhile but not terribly difficult exercise. I think it shouldn't be too hard to say, well, how far can we extend this? Can we do this for non-cyclotomic families of number fields? It would be enough to just find, like be able to write down or analyze or computationally find a good enough basis of the log unit lattice or some dense sublattice of it. So if you can do that for some nice family, you'd have a solution. And then hard is actually give a bound on that finite index that we know. So open for 100 years, but why not now, right? So here's a good reason, or maybe a good reason to actually solve this famous Weber class number problem. Right? That's all. Thanks.